So we've met the four individual gas laws, so Boyle's, Charles, Gay-Lussac's, and Avogadro's, and we've met the ideal gas law, but sometimes it's overkill. So although the ideal gas law will always work, sometimes it's kind of more of a pain than it's worth. And if you look at the ideal gas law, it's quite common for us to change the pressure and the volume and the temperature of a gas. And of course, R is fixed, so R you can't change at all. But it's very common for the number of moles to be unchanging. And so that allows us to go ahead and rewrite the gas law in a combined form. We can take P and V and we can divide both sides by T. And so PV over T is equal to N times by R. And if the number of moles doesn't change, then that's a constant. So assuming N is the same. So as long as you don't have a hole in your balloon or whatever you're dealing with, right, that can let gas in and out, then you can probably assume that the number of moles doesn't change at all. So that allows us to write pressure, volume over temperature before is equal to pressure, volume over temperature after. And so this is what they call the combined gas law. So let's go ahead and try this in a problem. So the Bermuda Triangle is a sort of a spooky place, I suppose. There's lots of stories about ships going missing and airplanes disappearing, and it turns out that one possibility is that there's an awful large amount of methane gas at the bottom of the ocean, and it's normally frozen, but every now and again there's a little tremor, and that methane can rise to the top. And we can use the combined gas law to figure this out. And so here's why this is such a problem. It is quite cold at the bottom of the ocean. At the bottom of the ocean, it might be a cool, say, -4 degrees C, and at the top of the ocean, it might be a much warmer, maybe 3 degrees C, let's say. And if you're wondering why it doesn't freeze if it's -4 degrees C, well, it's under a lot of pressure, and there's a lot of dissolved things that kind of suppress and lower that freezing point. And so we can go ahead and we can take a little bubble of methane gas, and here's our bubble. We'll draw it in red. And of course, one problem with methane is that it's quite flammable. And another problem, right, is that it will, if it gets to the surface, right, it can kind of move all the oxygen out of the way. And if you're up there, you might suffocate. So maybe we want to know what is the volume of that bubble when it reaches the very tippy top of the ocean. And we also need to know some pressures here. So it turns out the pressure at the bottom of the ocean is kind of large. Maybe it's somewhere on the order of, 17 atmospheres. And maybe at the top of the ocean, maybe it's something like 1.1 atmosphere, maybe just a little bit below the surface here. And so we can use the combined gas law in order to calculate the volume of that bubble of gas right at the top of the ocean. And how are we going to do that? Well, we can take our combined gas law. We can take our P1, which is our initial pressure. That would be our 17 atmospheres. We can take our V1, so V1 would be our 1.5 milliliters. And we can take our T1, well, actually that's a little T1. So in order to make it big T, right, so we need to add 273 to it. So 273, add -4, right, that is 269 Kelvin. So we got that. We've got P2, so P2 is that 1.1 atmosphere. So let's check that. V2, well, that's what we're solving for, so we need to figure out the final volume. And 3 degrees C, that is little t2, so little t2. So if we want big T2, we need to add 273 to 3, that's 276 Kelvin. So at this point here, we have everything but V2. So there's a couple of different ways to do this. We can cross multiply our equation, so we can bring the bottom of one side to the top of the other side. So that gives us P1 V1 times by T2 is equal to T1. So we've brought that from there to up to here, times by P2 times by V2. And why did we do that? Well, we were trying to find V2. And so now we are ready to find V2. And we do that by dividing both sides by T1 P2. And so y T1 P2, well, that cancels there, and leaves us with just V2 by itself. So we've got V2 is equal to P1 V1 T2 over T1 P2. And some people don't like this because it's kind of untidy, isn't it? So we've got 1s and 2s on the top and 1s and 2 on the bottom. But that's just the way the math runs out, I suppose. So we can go ahead and just push all that up a little bit there, and now we're ready to crunch numbers. So V2 is equal to P1. So let's see, P1 was 17 atmospheres. Okay, that's pretty high pressure. And V1 was our 1.5 milliliters. Okay, our T2 we figured out was 276 Kelvin. And we're dividing all that by T1. So T1 was our 269 Kelvin. And P2 was our final pressure, and that was our 1.1 atmospheres. And we got a nasty lot of units here, but it turns out that the Kelvin cancel and the atmosphere cancel, and we're left with milliliters, and they're on the top. And so that makes me feel much better about this problem, because I would expect a volume to have units of milliliters. And if I saw milliliters on the bottom, I would start to worry about my rearranging. So I can go ahead and grab my TI-83, or sorry, TI-30, and I can plug this in. And again, be careful with our bottom here. We've got two terms multiplied together, but we want to divide them both into the top. So use parentheses or divide by 269 and hit equals, and then divide by 1.1 and hit equals. And I go ahead and I get to two significant figures. I get 24 milliliters. And so if you remember, our bubble started at 1.5 milliliters. So that's pretty darn small. And at the end of the day, right, it ballooned out to 24 milliliters. So those little bubbles of methane at the bottom of the ocean, they get shaken free and they reach the top. They've expanded by almost 20 times their original size. So that is one possibility what makes the Bermuda Triangle such a dangerous place.